Hello, calculus fans. Let's talk about another scientific application here involving biology this time. We're going to talk about population growth. So what we'll do is we'll let n, which is equal to f of t, be the number of individuals of a population at time t. So this population could be an count of animals, plants, bacteria, anything like that. So what we'll say is that the change in population between t1 and t2 is delta n. So it's an increment of the population. How much does the population change? So that's f of t2 minus f of t1. And that enables us to actually write down an expression for the average rate of growth during this time period, where t is between t1 and t2. So our average rate of growth is delta n over delta t, and then it's the same expression we keep getting, f of t2 minus f of t1 all over t2 minus t1. And again, this is an average rate of growth. This is not a calculus thing. And of course, we convert it into calculus by calculating an instantaneous rate of growth. So we're going to let delta t approach 0. This is the usual thing that we've been doing. So now we're going to get the growth rate. You could say, if you like, the instantaneous growth rate. That's the limit as delta t goes to 0 of delta n over delta t. And that's dn over dt. That's a derivative now. Well, let's do a specific example. So a typical scenario that we run into is population of bacteria. And let's suppose that we've got a situation where our population of bacteria exists in an environment where they have unlimited food. Eventually their food will run out, but at least for the beginning they have an unlimited supply of food. And let's say we're able to sample the population and figure out how many bacteria we have. And we're able to determine that every 3 hours their population doubles. So let's suppose that our initial population is some number n naught, and we're going to measure time in hours. So if we do that, we can actually measure what the population should look like after 3 hours, after 6 hours. Because remember, the population is doubling every 3 hours. So at the beginning, we have n naught, and then 3 hours later, we've got 2n naught. That's f of 3. And every 3 hours, we experience a doubling in the population. This actually enables us to write down a general formula for what the population is. F of t is equal to 2 raised to the t over 3 n naught. You should be able to see that as we plug in values like 3, 6, and 9, that it gives us the appropriate doubling every 3 hours. You can see if you plugged in 12, it should have doubled 4 times, and you'd have a factor of 16 out in front. 16 times what the original population is. Now we can do the calculus. We can say that the rate of growth of the bacteria population at time t will be given to us by a derivative. So we can say that dn by dt is equal to the derivative of 2 to the t over 3 n naught. So we just have to differentiate this, keeping in mind that n naught is just a constant. So really, we just have to worry about differentiating t raised to the t over 3. Well, 2 to the t over 3 is an exponential function, so the derivative of that is itself. Of course, we do have to multiply by log 2 because the base of the exponential is 2. And then the 1/3, well, that comes from the chain rule. Now we can put some numbers in. Let's suppose we start with an initial population of 2,000, and then we're going to ask, what is the rate of growth after 5 hours? So essentially, we're just going to plug in these values. So we're going to plug in t equals 5 into this derivative. We're also going to put a 2,000 in place of n naught. We can use our calculator to work out the value here, and it turns out this works out to about 1,467. So now let's say what this number represents. The interpretation of this number is that after 5 hours, the bacteria colony population is increasing at a rate of 1,467 bacteria per hour. That's how fast the colony is increasing. It doesn't actually say what the bacteria population is at that time. You would have to go back to the original expression here to figure out what the population is. This is telling us how fast that population is growing. That's all for now.